So first of all, I would like to thank Professor Ricardo Reis for the kind invitation to chair this session at this workshop. It's always a pleasure to animate sessions between Brazil and France, and more especially between south of Brazil and Bordeaux, such as we have the cachaça from Porto Alegre, and of course, the wine from Bordeaux. Okay, so Marcelo de Souza received his bachelor, his master and PhD degree from Universidade Federal do Paraná, with a small detail for a PhD degree, that he's got it in collaboration with the University of Bordeaux in France. That is why he's not only specialized or an expert in electronics, but also in wine testing. Since last year, he's associate professor at Universidade Federal do Paraná in the group of integrated circuits and systems founded by Professor Mariano. Now, back at Curitiba. His interests are Baiado and the football club Atlético. But for research, his interests include radiofrequency integrated circuits and radiofrequency system design for wireless communication. Marcelo, the floor is yours.
Thank you, Professor François Rivet. I'm very glad to be here. Thank you, Mr. Ricardo Reis, for the invitation. I'm especially glad to be in an event of the university of my state, the state I was born. So I'm a gaúcho as well. So half of my life I've lived there. And I'm very, very happy to be here. So today we'll talk about the adaptive RF amplifiers and the using wireless communications. This I would like also to thanks Professor André Mariano and Professor Thierry Thaïs from Université Bordeaux. So for me, it's very, very important. Here we have the logo of all the universities and institutes that collaborate in this work. So we'll talk about why we need a reconfigurable LNA, or we'll talk about LNAs, low noise amplifiers, and why we need this. Why CMOS, why the reason, the context of this need. Our wideband design methodology and the implementation we did with two reconfigurable low noise amplifiers. And then we will summary up. So some of the reasons we are doing this is of the future radio challenges. We have growing demand for smart devices, battery life. So we have to be single chip and multi-standard, and you have to have a low area consumption of silicon. So we are living in the age of the connected devices. In 2020, we have around 26 billion network devices, almost 3 per inhabitant on Earth. So more than 40% are mobile. The device is growing. The device number is growing 9% per year, and the mobile data traffic is growing 50% per year, and video represents almost 80% of the data traffic. So by 2022, we'll have a 50% of the internet traffic from smartphones, with 30% annual growth, and 55% video capable devices are mobile, with 8% annual growth. So this says us that we have increasing need for mobility, low power consumption, and large bandwidth. Talking about bandwidth, we are surrounded by a multiple standards, communication standards. So we have GSM, UMTS, WiMAX, Bluetooth and the Wi-Fi's and so on. Now we are talking about the 5Gs, and so this occupies a large bandwidth on the spectrum. And our mobile phone, they currently use multi-chip solutions where we have different chips on the devices to do different standards. So Wi-Fi, one for Wi-Fi, Bluetooth, and one for GPS and GSM and so on. The UMTS, LTE or so. So the idea today, they use we use multiple chips or multiple chips inside one package. There are several solutions, but they use multiple transceivers, and these transceivers usually are narrow band and tuned to one frequency only, and the frequency that they have multiple transceivers tuned in each frequency that the standard requires. And usually this is implemented with a lot of inductors. And inductors are a thing very difficult to reduce the size. So they occupy lots of space in the silicon chip. So this is not a good solution for the next generation of radios. We have to go further. And if we look at the consumers, the buyers of smartphones, what they value most is battery life. So is one of the most important things on one device. So we have several options to increase battery life. One is increase the energy stored, or we can reduce the consumption of the processor or the circuitry. But as we can see here, the battery doesn't evolve as quickly as the other technologies. So we are a little bit stuck on terms of energy storage. So there's no Moore's law for batteries. We have about a 3% growth per year max. So how to improve battery life? Reducing power consumption. So we have to focus on the consumption of this circuitry. So the idea of this work is to have an amplifier here that is in the low noise amplifier is the first element of a chain reception, and it usually is as the theory goes, is the most important in terms of noise. All the noise applied that is generated or inserted on the signal in the first step will not be removed afterwards. We can increase gain and so on, but the noise we cannot remove. So the first stage has to be very, very low noise, has to contribute to very little with noise. And the idea is to have a reconfigurable LNA amplifier that can be switched by the DSP. So digitally, it can switch parameters and change the behavior of the amplifier or the receiver. Change the behavior of the receiver as needed. So to focus, if we are receiving one standard, we can focus on this standard or the other, and we can configure it on the fly. So the idea is to have adjustable wideband response. So we can sense all the standards, know what standard is transmitting, and adapt the gain in this wideband, or we can switch to a narrow band and tune to one specific standard. So we have more flexibility. And another important thing about the LNA is that, different from the PA, the power amplifier that transmits signal, the LNA is always on. So PA can be enabled only when it's transmitting the LNA. We have to always turn it on and receive signals and sense what is going on. So, and there's another problem, that is the linearity, because as a mobile device, this receiver can be close to the source of the signal, or can be far away from it. So the signal can be very, very weak, or can be very strong. And strong signals are a problem regarding linearity. So we have to be able, if we can trim these different parameters, so we can adjust gain, adjust the noise figure, and adjust the linearity, the 2IP3. This will be a better radio than the fixed one. So we are focusing on this part. So the idea is that we have multidimensional or real-time power consumption optimization. So if we need some, in one moment of the time, we need a gain, a different determined gain or linearity or noise figure, we can switch the configuration of the amplifier, and this way we can be adapt and use the lowest possible power consumption for the different requirement over time. So we have several specifications of this standard. So Bluetooth, WiMAX, LTE, UMTS. So different standards have different requirements regarding the noise, the linearity, IP3, and the gain. So so standards are more relaxed in that, or noise figure, more stringent on noise figure, or more stringent on linearity and on gain. So we have to be multi-standard with one LNA. We have to meet these standards requirements. So here we will talk about our proposed methodology. So we evaluate several different topologies, and here we can see the pros and cons of each one, and we chose our topology to be feedback one. So we have a feedback path. So we are focusing on silicon area, the control of the performance, the low noise and gain and bandwidth. But one of the cons of this type of architecture is the power consumption. So we are focused on increasing this. So for this, this is the schematic view of our amplifier. So we have a direct amplifier and a feedback loop amplifier. This is an active feedback, and we can model it as a gyrator. Gyrator is a virtual inductance, so we can use to do the matching of the input without the use of an inductor, so we can reduce the size of the circuit. And we have here two different points of control in this topology, where one we can control the noise figure and the other to control the linearity. And this is the simplified version of the transistor, how it looked like. So we have here a complementary inverter. So it's a PMOS and an NMOS resistor here to bias the circuit, and here we have an active feedback loop. So the circuit that has very few transistors and was implemented on Global Foundries 130 nanometer CMOS technology. So how we size the LNA? Our methodology was based on a strategy that was to tune the parameters, to scan all the multiple parameters, and because in this circuit we have 4 transistors, we have capacitors, we have bias voltages, we have multiple parameters. So is a problem, and we have width, length, and number of fingers of the transistors, and we have several objectives. So we have gain, noise figure, linearity, power consumption, bandwidth, and so on. So this is a problem of a multiple variable and multiple objective optimization problem. And if we look at here, we made curves of, for example, the width of the transistor, different transistor here, M1N and M2, and we can see the different goals. So gain, bandwidth, product, and matching, response, the product, the power consumption, the noise figure, and linearity. It varies. There are different best values. So how can we optimize? We can say, well, we can optimize for better for low noise figure, or we can optimize for power consumption. These are antagonist objectives, or we can increase linearity. So we have multiple goals, how can we define how we are going for the best spot? And in this we can see here there are other parameters. Here is the width of the transistor, but here we can have the feedback resistor, have the bias current of the feedback, and so we have multiple parameters and different best values. So to solve this, we use the FOM, the figure of merit, that we are presenting here. So where we have, we want the maximum gain, so it's in the numerator here. The linearity we have to be the best, the greater the better, and the bandwidth, the greater the better, and the noise figure on the denominator and a power consumption on the denominator. We have to minimize this. So we use this and the requirements from the standards. So each standard have a requirement. We use this as also restriction on the design, and we used a simulation assisted method. So we simulate all the possible, or most of the possible combinations, and plug in this simulation results and measure all the parameters, the design goals. We call FOM, and then we restrict this with the specification, and found the region where the design is best. So we first simulate the changing the parameters, measuring the results, and then out of the surface of the possible configuration, we discard the region out of specification, and we have the optimal solution for this case. So that maximize the FOM, meeting all the standards. And we implemented this to reconfigurable LNAs. And here's the version of the first one that was implemented. We have a DAC here to control the current, the bias current here on the main amplifier, and the feedback. We have also current reconfigure current here to change the current of the feedback loop, and so in have a buffer at the output, so we can measure. This buffer is only needed for measurement, and you have here a capacitor of the pad that was modeled as well. So here is the chip layout, and we can see here there are the pads on the signal pad, and the circuit, the core circuit is just here. So we can see all the rest here is the buffer that is not related, not needed in a real implementation, the decoupling capacitors and ground plane and so on. But so we can see that the size of the size consumption of this LNA is very little. So it's 0.77 square millimeters. And so it's the size of the pad, almost the size of the pad, is a little bit smaller. It's very low in power consumption. This was produced with Moses system, and it was measured at the IMS Bordeaux. So here we have a photo of the chip and the measurement equipment, and with this we have 3 operating modes. We called mode 3, that high linearity mode, with power consumption of 7 milliwatts. That was considered at the baseline. The low gain mode, the mode 2, that consumed with 3.1 milliwatts of consumption, and the low power mode, mode 1, with 1.5 milliwatts of consumption. So 5 times reduction can be achieved, only changing the configuration. Here we can see the input impedance of these LNA on the 3 different modes, and we have to be better than minus 10 dB to be matched with the input. And here we can see that this, in the worst case, this LNA reaches 2.2 gigahertz of bandwidth, of input matching bandwidth, and in the mode 2, mode 3, we reach more than 5 gigahertz of bandwidth. In all on configuration, we are better than minus 9 dB. This is measurement, and the red line here is the port layout simulation. So we can see there's a good agreement between the simulation and measurement. Here we are seeing the gain of the different modes and the simulated value. And the simulated value was a little bit higher, but we can see that we don't have much control of the gain. This topology doesn't change a lot of the gain. The gain is about 20 dB. have a high gain, but we cannot change much from one configuration to the other. We saw that it's unconditionally stable. That is a problem with active feedback amplifiers, and we have control about 3 dB from one mode to another, and we saw here we have the NF, the noise figure of the different modes. So the best configuration here, we have a minimal noise figure close to 2 dB, and again a good agreement with the pulse layout simulation. So we have noise figure from 2 to 2.7 dB. Worst case, we have 3%, less than 3.7 dB for all configurations on the just up to 3 gigahertz, and an NF control range of lower than 1 dB. And one of the other objectives of this design is linearity. Here we can see different in modes of operation of the LNA regarding linearity. So here we can see the IP3 and different configuration in terms of the feedback and the different modes of operation. And here they have the IP3 according to frequency. So we have, again, good agreement between the PLS and the measurement. We have high linearity mode that have more than 16 dBm to IP3. And worst case, IP3 is better than 4 dB in all configurations. So we have low dependency on the frequency and a strong dependency on frequency gain roll off. And the IP3 control range is about 6 dB. So here we have different the different wireless requirements. So we can see that in all different modes, one of the modes are always inside of the requirements, meeting the specification. The WCDMA is the most stringent on noise frequency or noise figure requirement. It was not met, but it was very close. The high gain, for more than 50 dB, is enough to mask all the remaining stages noise. That is one of the objectives of the LNA. And the linearity met all the requirements in all configuration and standards. Here, if we compare with the state of the art or with some of the most important LNAs at the time, we can see here that the no noise mode of the chip is 2 dB noise figure is very good. Is worse than some of the competitors, but all the others, the better ones, are using better, more recent technologies, or 90 nanometer or 65 nanometer. We are using 130, and these others that have low noises, they have bad linearity. So we are balancing here. One of the here we have a very high power consumption of 18 milliwatts. So if we look at all the results here, we can see that we have a figure of merit, FOM, that is better than all the other competitors. And if we use the area of the circuit as we plug in the area, the lower the better. We see that this balance between low noise, bandwidth, and gain and linearity. This proposed architecture is a promising one, but it has some problems. It didn't have the bandwidth we wanted, because we have standards that are wireless standards that occupy the 5 gigahertz or more. So we would like to go to 6 gigahertz of bandwidth, and this architecture was not good enough. So we only reached at most 2.1 gigahertz of bandwidth, and that is most due to the parasitics of the 130 CMOS technology. So one of the solutions we came up was to this time to use an inductor and use an architecture topology of shunt picking. So we implemented that. So we used the single stage. We took the single stage generator that we developed, and we plugged in another stage, and this stage will allowing us to control the bandwidth, the gain, and giving us the possibility to turn it off and only let the first one be on if needed. So we used this two stage. So we took the first one and we add the second stage here. This one has an inductor, and so it occupies more space, but it allows us to switch the bandwidth between wide and narrow band. We can we can do narrow band tuning, wide band tuning. We can choose gain and NF. So we add more to the amplifier. So here is the schematics of the transistor used. So the first one that we already discussed, and this one is the second stage we introduced. So here we have a bypass switch that can allow us to use only the first stage if we wanted. So here are the different parts. And here we used a DAC to control the current, and several DACs here to generate the bias of the first and second feedback loop and the second stage. And we use the digital serial to parallel interface that we could send digital commands and plug to all these DACs, and so we can control the mode of operation on the fly. So we sent a digital signal, and this digital signal switched the DACs, and the DACs would change the modes. And this is the layout of our LNA. Here we have the capacitors, transistors, capacitors, decoupling capacitor, the feedback. So this is the feedback transistors. Here we have these inductors, so you can see the enormous space it takes on the chip. And here we have the small size transistor, and with the feedback transistor, the second stage transistor. And this was also implemented and measured. And here's a photograph of the chip. And as we have 16-bit here to configure our different decks. We have 65,000 configuration possible. So we reduced the combination because not all of them would be significant, and so we reduce it to 96 performance configuration was relevant. And here we can see the size of this is the original generator, the bias generation decks, the digital interface, the second stage picking stage, the output buffer. And the area of the core, including all of this, is about 0.1 square millimeter. Now here we have some of the configuration that were measured, and we have matching frequency of here we are seeing the input impedance matching S11, and the S11 is better than a minus 10 dB for at minimum 3.4 gigahertz and maximum over 8 gigahertz. So depending on the mode, we have more or less matching of the input impedance, but all the configuration remain above minus 8 dB. And here we are seeing some of the gain configuration. So we have, this is the different gains we can reach. So we have here 16 highlighted modes. The wideband mode 6B, where we now reach the 6 gigahertz bandwidth with a max gain of 24 dB and gain control of 12 dB. And if we bypass the second stage, we are left with this this output, and we have less than 3 gigahertz bandwidth and max gain of 23 dB and gain control of 5 dB. And here, if we combine the narrow band, when we are not using, we are tuning the inductor in a single frequency, we have 1 to 3 gigahertz of bandwidth and max gain of 24 dB, almost 25, and gain control of 21 dB. So and on terms of noise figure, again, we are close to 2 dB, the best on the best configuration, and we have a good agreement. And so here we have 9 of the modes: wideband, narrowband, and bypass. The worst case is the best case is 2 to 4 dB on mode WLN, and the worst case is more than 11 dB when we are narrow band and we have no gain. So this is the worst case of the LNA in terms of noise figure. In noise figure control, range of 9 dB. And in terms of FP3, is not as linear as the cheap one. We are only the generator like an LNA, but the best case is minus 1 dBm, the worst case minus 9 dBm, and IP3 control range of 8 dB. And here we can see that the sensibility of the linearity according to frequency and bandwidth. So it's practically insensitive to frequency and is sensitive to spacing, the delta F of the carriers that we are testing. but is resistant to in-band blockers, coadjutant blockers. So in terms of power consumption, we have the max power consumption of 15 milliwatts and the lowest power consumption of 3 milliwatts. So again, 5-time reduction. And from mode here, from two of the modes, and here another. We are using wideband, a wideband configuration. We go from 14 milliwatts to 5 milliwatts, again at 3 times reduction. And in terms of NF, all the standards, the wireless standard we're proposing are met. The Wi-Fi 5G is close, and the same for the WCDMA. The gain met all the standards. The IP3 all but the WCDMA. So a more linear mixer is needed in the chain to solve this, to overcome this, and so we have several configuration, we have flexibility, and the DSP can choose the best mode for each moment or each configuration. So here we have a summary of the different LNAs and the chip to measurement here. So we have more bandwidth here. Before we only went to 2.1 gigahertz. Now we have reached the 6 gigahertz, and we have still a very low noise figure of a 2.1 in 130 nanometers. So one of the best here of this technology. And we have two that are better, but in a better technology, a newer one, more recent. And in terms of gain, we have a very good gain here, 24 dB. So we have, if we compare with this one that had 25 dB, it consumes much more power than this. The solution. And in terms of IP3, again, we have a very good linearity, and another one that uses more power, is more linear, but uses more power. And so we have, if we look at all the capability here, we can see that we have achieved a good solution. Well, we have these other types of here there's a very low power consumption. Even in our lowest mode, they consume very less, but they are less linear. So there's a compromise. So we took here if we look at the FOM, so we see that our proposed circuit is very good and balanced on all the different performance goals of our LNA. So that's it that we have for today. I would like to thank you all for listening to this talk, and I'm glad to answer some questions.
Thank you very much, Marcelo. So as we have a small lag between the live and what is broadcasted on YouTube, so please, you can ask your question to Marcelo directly in the chat. And I'm going to start with the first question. So as you mentioned, your circuits are depends on many parameters, and you try to find always the best trade-off For instance, between the linearity, the noise figure, the gain, of course, and depending on the communication you would like to have. I mean, in terms of frequency, bandwidth, it's always large band, but of course, you're gonna use it for a given communication, modulation, etc., etc. I was wondering if we can take the best worst performance, see what I mean, the most degraded one, but just the one that is sufficient to have the most optimized power consumption. And I guess it's quite hard to find which parameter, biasing, voltage here and there, etc. And this is my question, and it's not an analog one. Have you considered artificial intelligence, or at least machine learning, to do the job for you and to control your circuit?
Yes. Yeah, we have considered. At the moment, the design methodology was not the point of the focus. But the focus was to get a very low area and so on, and the methodology came with it. And one of the including after this work, there's a student that's working on to plug the simulator, the RF simulator with the artificial intelligence to make this choice automatically for us. That's the holy grail of the RF ICs, but we are working on that. Yes, that's. But by the time I was working, this was not. There were not enough time. We had the schedule, the tape out, and so on. So, but this is in the workings at the moment.
Yes, and also the other side of that answer is that artificial intelligence can design the circuits for us, and we can lose our job. But that's a whole debate that can stay in Porto Alegre for the EDA guys, of course. We have a second question coming from Luis Eduardo Palomino Bolivar. What is the maximum switching speed between the amplifier settings?
We tested that. It's about milliseconds. It's very, very fast. Doesn't milliseconds or less than 1 millisecond. The speed. Okay. So it's not a problem to change on the fly. Well, in a commercial product, maybe, and it cannot switch faster. Most is because of we used a serial interface that was low frequency. So the limitation is on the digital part, and not on the analog part. So, but it's quite fast enough to be used on a RF receiver.
Okay. So if you have any other question, please put it on the chat. I have a second one, so I'm waiting for others, but I have a second one. It's about, so you have presented some LNA, and so far I've seen that it's a large band. Again, you try to do the most you can, but the power consumption, etc. And what is critical for LNA is, of course, the noise figures and all this linearity. What is trendy now is, since 5 years, the use of end-pass filter. Have you considered to assemble these two and benefit from end-pass filter to do the job you don't want to do in the LNA?
Yes. The end-pass filter is actually was after this one was also the one that was being developed, was developed by Gabriel at the EMS. So yes, we used the end-pass filter idea. Yes.
Okay. Yes, I think it's a new trend to do that.
Yeah.
I don't see any more question, and I think it's already the afternoon, middle of afternoon. And in France, I must say that it's 7 p.m. and it's a very important time. As you know, it's aperitif time, and it's a day off here. So I consider that we can close the session now. I would like to thank you again very much, Marcelo, to have presented the work from Curitiba, and it's always a pleasure to be there with you in Brazil. Thank you so much.
Pleasure was mine.